All right, so, oh, my webcam's doing something weird, okay. Good morning. Final exam schedule, that's what we were talking about. So the final exam, and yeah, so there are 5 assignments due. Assignments for 2.2 through 2.6 are due tomorrow. But there was a whole pile. I just piled them up and made them all due for the 12th. That's not true. I just changed it so that there's just those few. I
saw that. I saw that and I'm like, oh my God, thank you.
I just kind of keep pushing them forward. So don't worry if it's not something that we covered last week, then I will shift them. But sometimes I'll need a reminder. So, and someone reminded me yesterday, and I thought I better change that. So the final exam is on April 21st. Let me just make sure. From 1 till 4. And of course, we'll talk more about it then, but it'll just be online, just like everything else, and easy peasy. Then we're done. And then assignments 2.2 to 2.6 are due tomorrow. At midnight, always at midnight. So, okay, great. I feel like there was something else I was going to mention. Is there something else? If I have little things that I need to bring up, I usually jot them down. But I don't have a consistent place where I jot them down, so a little bit tricky. Making it harder for myself. Okay, well, no worries. So we started section 2.7 last day. So just for some review, we finished transformations of functions, which is actually section 2.6. But we started and did the majority of it last week, so that's why I made it due tomorrow. But it's also to kind of keep you on track, because we do have our test 2 coming up, but we're going to cover a lot of material before then. So I just want to kind of keep you on track here. So 2.6, we finished it off last day. So you'll have everything that you need there, but we talked about combining functions. So combining functions, and we did a few examples where we combined functions. So what we're doing is we're taking small functions and we're combining them to make new functions, right? So now we have a new, bigger function. We can combine functions algebraically. Oops. Algebraically, right? Such as f plus g of x is the same as f of x plus g of x, right? And then with domain, with the overlapping domain. So when we're combining functions algebraically, right, we can add, subtract, multiply, or divide functions, and I will get you to do problems like that, and I will get you to find the domain, or the domains of all those functions, so those new functions. And then we just started talking about combining functions. We don't typically say compositionally, but compositions. And so, but just to match algebraically, compositionally. composite functions. That was where we had this kind of notation, right? F composed with G of X is the same as, and I said, well, I kind of read this as F of G of X, because that way when I say it, even though that's not what this O stands for, right? So this O stands for composed with. Okay. But when I say it like F of G of X, well, then I can just write it out the way I'm saying it. So F of G of X. Okay. So what that says is take G of X and put it as and use it as an input of F. So F of G of X equals F of G of X. Use G of X as an input into F of X. Okay. These can be kind of tricky, and so I want to do a couple more examples, and I've got a note here of 56. Let me just go back to our notes from last day, and what do you know? Try 56 on your own, and we will use it as a review next day. So let us go and try 56. So here, I'll just grab them again. And what I said last day was, don't worry about the domains, because the domains can be quite tricky. It is something that you can kind of work at and practice, and the solutions that you have will have the domains. So it is something that you can think about and kind of try, but it's not something that I'm going to test you on. Okay, so it's not something that I want to spend any time on confusing you here. I just want you to be able to make composite functions. Okay, so we're going to do 56. Okay. And I guess this is the, I guess I said it was for review, so let's, all right, fine. So 56, I have F of X is 1 over root X, and G of X is X squared minus 4X. Okay. So what we were doing last day, because we need to, I was about to talk about the domain. I was stuck in the combining functions algebraically. So don't worry, but let's talk about just the domain here, just to get in the groove again, right? So here, F of X, right, has a domain. Well, I've got a square root and I've got division. So I need to make sure that X is greater than or equal to 0, right? So it has to be positive. And then I need to make sure that I'm not dividing by 0. So then X has to be larger than 0, and it can't be equal to 0. So note the domain of F of X is X has to be greater than 0. A polynomial it will always have a domain of all real numbers, right? So there's no restrictions on the inputs of G of X. And so because there's no division and there's no roots, right? No even roots. And so the domain of G of X is from negative infinity to positive infinity. Maybe I should write X greater than 0 as an interval 0 to positive infinity. not including 0. That's just for practice, right? So we're not going to do the domains, because what happens, well, if I am putting in a function, so for example, let's do this first one. So we're asked to find the functions f composed with g, g composed with f, f composed with f, and g composed with g. Okay, so let's go ahead and start doing that. So f composed with g of x is the same, and I like to rewrite it as f of g of x. Okay. So that's going to be your first step, is just kind of rewriting it like this. Okay. And then I showed you 2 different approaches that you could do. You could fill out the f function and keep your x's as g of x, and then replace your g of x with your g of x. Or you can put in g of x and then fill out your f of x, right? So it doesn't actually matter. And the only thing is, I wouldn't recommend doing both at the same time, because that can be really confusing. So what I'll do is I'll do 1 over the root of g of x. And then in the next step, I'm going to replace g of x with x squared minus 4x. So I get 1 over the root of x squared minus 4x. Okay. Here, what I will say is, or I'll show you both ways, right? Or if you prefer, then you could have f of x squared minus 4x. Okay. So now I'm plugging in my g of x first and then fleshing out my f. Whereas here I put my f out there and just kept the input as g of x and then replaced the g of x. So now this becomes 1 over the root of x, which is replaced with x squared minus 4x. Okay. Notice that you arrive at the same result. So it doesn't matter which one you do, right? Just pick one method that works for you and just stick with it, right? Pick one method and stick with it. Or, I mean, you can bounce back and forth if you want to, but just so you're not confusing yourself later on, right? Just kind of start to get in the habit of doing one or the other, whichever one makes more sense to you. Okay. I tend to go for this first one. That's not always the case. Sometimes I'll go for the second option where I put g of x in first, but this is more of a personal matter, so you'll have to decide what you like best. But then you can just go ahead and do it. Okay, so this is my final answer. I don't see any simplification that I can do, and that'll be the case a lot of the time, right? When we do these, there's not necessarily a lot of simplification that you have to do. So now I need to find, I keep wanting to find the domain. Why do I keep wanting to, I'm hung up on the domain. I don't want to. I told you guys we wouldn't do it. Let's just briefly talk about it, and then I'll try to forget all about the domain. Because I remember when I was first learning about the domain, I hated the domain. I hate finding the domain. I don't get it. Why do we care? Wow. Because it's all the possible inputs. Anyways. But here, because it's a little bit harder, let's just talk about it. So what we're saying is that g of x is going into f And so the outputs of g of x, right? So what we're saying is that, okay, anything can go into g of x, okay? But then I need to make sure that the outputs of g of x satisfy the inputs or the possible inputs of f of x, right? Because g of x is going into f of x, which means I need to restrict my outputs of x squared minus 4x to be larger than 0, not including 0, right? And so then you have these restrictions on x squared minus 4x being larger than 0, which you need to solve for x, which, and that's why it's a little bit tricky, because it's a little bit of a mind bender. Okay? So let's not do the domain. Let's just keep going. Compositions are hard enough. G composed with F. G composed with F of x is G of F of x. So like I said, I want to pick a method and stick with it. I'm going to write out G, but instead of having x's, I'm going to have f of x's, and then I'll put in my f of x. Okay. So I have f of x squared minus 4f of x. Then I can replace my f of x's with 1 over root x. So here I get 1 over root x squared minus 4 times 1 over root x. I'm going to be able to simplify a little bit. So let's see here. When I have these kind of rogue fractions, then I can simplify, right, by finding a common denominator. My dog's struggling. Anyways, let her figure it out. Okay, so what we have is, remember from our exponent laws, I can bring this square inside onto both of these. The square of the root of x is just x, right? But then over here, I have the root of x also as a denominator. So what I need is I need to find a common denominator. Sorry, I'm just gonna help her out just a second. You need a little bit of help. Struggle Central. Okay, so just kind of surveying the scene, right? I see that I have a root x. Yeah, well, I let her struggle for a while. So we've got the root x squared, but then I also see I have a root x. So knowing that, right, that I need to find a common denominator, then I'm going to just write it as the root of x squared. So I get 1 squared over the square root of x squared, which I know is x, but just to simplify the process a little bit, I get minus 4 over the root of x. So now I'm going to force a common denominator, but all I need to do is multiply this term by the root of x over the root of x to make it match. Because now I've got the root of x squared, which just happens to be x, right? But it's easier to see this way. 1 over x minus 4 root, and I guess I could just put it over that common denominator right away. Let's see here, 1 minus 4 root x all over x. Good. So here, right, now I have this new function, which I've composed from the two old functions, right, g and f. Okay. Notice that it looks really different, right? it looks really, really different from f composed with g of x versus g composed with f of x. Right, so they're going to be quite different. Okay, and so here, notice f composed with g of x does not equal the same as g composed with f of x. In fact, they're very different, I would say. Okay. So now I think we want to find f composed with f. We can do that, right? I can stuff the function into itself. And then finally we'll do g composed with g. So let's find f composed with f of x is f of x. Okay. Doesn't really matter how we do it, right? This becomes the 1 over the root of f of x, where f of x is also 1 over the root of x, right? So now this becomes 1 over the square root of 1 over the root of x. Okay. I'm going to need to rework these exponents a little bit, right? Recall that the root of x we can rewrite as x to the 1/2, right? And then if it's in the denominator, I can make the exponent negative to indicate that it's in the denominator. So what do I have here? This becomes, I can simplify this to 1 divided by the root of x to the negative 1/2. Right? Okay, but I can also rewrite that square root as a power of 1/2. So I get 1 over x to the negative 1/2 to the power of 1/2. Do you remember the exponent rules? If I have two exponents being multiplied together, I can just multiply across. And just remember, everything's coming into play here, right? We have to remember how to multiply fractions. We can just multiply across. And so what does this become? It becomes 1 over x to the negative 1 over 4. Right, so now it's over the 4th root, right? But it's 1 over the 4th root. If I've got a negative exponent, why is it negative? Okay, so it depends on what playing field you're on. So here, I'm just focusing on the 1 over root x. So 1 over root x is x to the negative 1/2, right? The negative says that it's in the, it's down in the denominator, and the 1/2 is the square root. Awesome, nice. And then it's I've kept it positive because I've kept it in the denominator. But what I'm about to do, you won't believe what happens next. Because I have a negative power in the denominator, well, I can bring that upstairs, and making it negative actually turns it positive. So here, right, this becomes the same as x to the negative 1 over 4, right? If I bring that upstairs, I have to negate it, but seeing this negative here, I can actually bring it upstairs and make it positive. So I get to x is to the power of 1 over 4, or if you prefer, the 4th root of x. Nice. Okay. Good. Whew, that's a biggie. Let's do g composed with g of x. Well, that's g of x. G of x was x squared minus 4x. So I have g of x squared minus 4 times g of x. And then I have to replace each of these g of x's with x squared minus 4x. So this becomes x squared minus 4x squared minus 4 times x squared minus 4x. I do want you to expand this out and simplify. And just remember that x squared minus 4x squared is x squared minus x times x squared minus 4x. So you'll need to do that expansion here. So I'm just going to emphasize x squared minus 4x times x squared minus 4x minus, I guess let's just keep it as it is for now, 4 times x squared minus 4x. Eventually I'll expand that in, so if you want to start doing that now, that's fine. I'm going to focus my attention over here for a little bit, and then I'll do the expansion over here. So I get x squared times x squared is x to the 4th. X squared times negative 4x is negative 4x to the 3 minus 4x to the 3 again, plus 16x squared. Pretty sure negative 4 times negative 4, yeah. And then minus 4x squared plus 16x, right? So you want to make sure that you bring in this negative as well. Whether you expand the 4 inside first and then bring in the negative, you can do that. Or if you're bringing in negative 4, you have to do it on both terms, right? So plus 16x. Whew, okay. Can simplify this a little bit. It actually looks like I've got decreasing powers of x already. So that's good, because eventually, right, if you're working with a polynomial like this, then you'll want to start writing your polynomials with decreasing powers of x. It just makes it easier to read and look more proper. And then minus 4 minus 8x to the 3. 16x squared minus 4x squared puts me at what, 12x squared plus 12x squared plus 16x. There, we did it. That's great. Okay. Let's do this the other way. So function compositions, of course, we need to know how to compose functions, right? Being able to put a function into another function is important. It's an important skill. Another important skill here is being able to take a big function and break it down into a composition of functions. And so we will also, and I'll call that the end of our review here. It wasn't, tons of review. It was kind of new, but we started it last day, so I'll call it a review. But so we will also need to be able to take a large function and break it down into a composition of smaller functions. So we will also need to take a large function and break it down into a composition of smaller functions. So this is something that we do in calculus quite a bit, is taking a large function and just kind of figuring out, okay, I've got all these functions in here, and I can actually break this down into a composition of functions, and that's going to help me solve more problems. because I can know what x squared looks like. I can know what 1 over x looks like, but I don't necessarily know what x squared over 1 over x looks like, right? So if we know what the little functions behave like, and we saw that in section 2.2, right, with that big blue box of kind of common functions, right? The root of x, 1 over x, x to the power of 2 to the power of 3, right? We saw that general behavior. So we can know those, and then if we're able to break down a large function into kind of smaller functions, then we can kind of have a good idea of the behavior. So let's go to these problems here. So I've got, just a little bit. We've got these kind of bigger functions here, not huge, but we're just starting. We want to express this in the form of f composed with a g, right? So I've got these new functions, capital F, for example, or capital G or capital H. So I'm going to decompose these into two smaller functions and rewrite it as a composition. So let's do, and there will be a few different options sometimes, right? So there will be options, and we'll kind of talk about what a good option would be, or like a better option would be, I should say. But there are lots of options. Let's start with 63. If I have f of x is x minus 9 to the power of 5, okay, it looks like I have a function that raises something to the power of 5, and then I also have a function of x minus 9, right? And so here, it looks like I have x minus 9 inside something to the power of 5. How are we going to denote that? So we want to express it in the form of f composed with g. So f composed with g of x is going to be x minus 9 to the power of 5. What if I let, right, so g of x has to be what's inside. So what if I let g of x be x minus 9, right? So here I'm going to let g of x be x minus 9. Okay. And then what does f of x have to be? F of x must be x to the power of 5. Right, remember, because we're putting g of x into f of x, so we just need one x to hold as a placeholder for that x minus 9, which is going in, right? So now I've broken it down into two simpler functions. Right, there will always be multiple ways that you could do this, but you want to avoid doing something like maybe you have let g of x be x and f of x is x minus 9 to the 5. It's true, but you didn't really do anything, right? You didn't decompose this function. You didn't make your life easier, right, by kind of tearing apart this function, right? Technically it's true, but it's not going to help you, right? So you want to kind of make your functions as large as you can, right? Or kind of as encompassing as you can, right? This is technically correct. Technically correct, but it won't help you simplify the function. Yeah. So though that's something that you can do, it's not something that I want to see, right? I want you to kind of make your composed functions, or the ones that are smushed together, as large as you can. Let's do 65. And I'm going to grab it from here. I've got g of x is x squared over x squared plus 4. Lots of things you can do, right? Let's see if we can kind of push the limits here. Let's see here. Is there anything I can do that's not letting g of x be x squared? Not really. I could let, no, I'm satisfied. If this is going to be f composed with g of x, then we're going to let g of x be x squared. What does that make f of x? F of x must be x over x plus 4. Could we? Wait, what else could we do? Right. Another option. Thinking outside the bun here, right? What if I let g of x be x squared plus 4? What would I have to make my f of x? Right, so now I'm inputting x squared plus 4. So then f of x, right? And this is a good exercise in just kind of, okay, so what do I need to do? F of x must be x minus 4 over x, right? Because if I'm letting g of x be x squared plus 4, then I must subtract 4 to make it just be x squared up top. But then in the denominator, I've got x squared plus 4, which is what I want, right? So you have options, and there's lots of different ways that you can break it down, right? I'd say this is probably the most obvious, right? Not very, revolutionary, but it works. Let's do 67 as well, which says that h of x is the absolute value of 1 minus x to the 3. Yeah, option 1 is a little bit more reasonable. Yeah. Yeah, this one's kind of a bit much, but it's an option. So if we have the absolute value of 1 minus x to the 3, I would say that the obvious choice here is letting g of x be x to the 3. You could even let it be negative x to the 3 if you wanted to. It just kind of depends on what you want inside your absolute value. So a lot of these are kind of depending on the scenario. What do you want to deal with? So here, if we're going to let this be f of g of x, we can let g of x be x to the 3, then f of x must be what? The absolute value of 1 minus x. Right? Or, right, depending on the situation, if you really just wanted the absolute value of 1 plus x here, then that negative would have to be absorbed by the negative x to the 3, right? And so it just kind of depends on what you want to deal with. Good. You'll see kind of down below here, I have labeled it as optional, but I think it would be a really good exercise, and I'm not going to test you on it. It's not something that I expect you to be able to pull out, but to prepare you for calculus, right, then you might want to extend it to 3 functions, right? Compositions with 3 functions and bring down compositions of 3 functions, right? So now we've got 3 functions instead of just 2. So it would be a good exercise, but it's not something that I'm testing you on. All right. So let's move on to the next section, which is related. It's not going to feel related yet, but it is. Let me know if you have any questions, though, about that, because compositions can be kind of tricky, I find. (2.8) is on one-to-one functions and their inverses. And their inverses. Maybe we should take a little break before we start a new section. How about that? It's a little earlier than usual, but how about let's have a break until 8:50. You can go caffeinate or whatever you want. 2.8, let's do it. All right. So, delete. We're going to talk about the inverses of functions, which are just kind of how do you undo a function. And so we've already kind of solved for x, and what we're doing there is we're solving for x by picking away and moving things over to the other side, right? The other side of the equal sign. And it's kind of similar. So what function would undo the other function? And so a function is invertible, meaning it has an inverse. Not all functions have an inverse. Has an inverse if it is one-to-one. Okay. So what we need to, oops, end bracket there. What we need to know is, okay, well, what does it mean for a function to be one-to-one? So in order to find the inverse of a function, we first need to check that it's one-to-one. So we can prove it mathematically. I'm going to skip that this year because I want to just get to the nitty-gritty. And so there are a couple of ways that we could prove that something's one-to-one, but let's just talk about what it means to be one-to-one. So from your handout, let's see here. And you know what, I'm not going to grab that image. I'm going to make my own. So a function is called one-to-one if no 2 elements have the same image, meaning if no 2 elements have the same output. Okay, and so This is a function is 1-to-1, 1-to-1 if no two different values of x yield the same output. If no two, and I'll put in brackets here, they have to be different values of x or inputs yield the same output. Oh, forgot you. So graphically, let's look at some graphs that we know. Okay, maybe I've got the root of x. Okay. What that's saying is that, well, it looks like each of these outputs are unique, right? For each value of x, there's no two values of x that yield the same output, right? And so here, this is 1-to-1, is 1-to-1, since no two values of x yield the same output. Output or y value. Okay. Whereas if we think about kind of our go-to x squared, right, if I have something like this, x squared, for example, right, let's say this is the root of x. Well, so now what I'm finding is that, well, I've got these same outputs for two different values of x. So here and here, right? So what we're going to say here is that this is not 1-to-1, not 1-to-1. And it makes sense. You can think about it, right? If I put in -2 squared, I get to 4. But also if I put in 2 squared, I also get to 4, right? And so two different inputs give the same output. So not 1-to-1 because two different inputs yields the same output. Okay. So we can prove this mathematically, right? And what we would do is we would say, okay, I'm going to pretend that x1 and x2, or I usually use a and b are not the same. Then if I put in f of a and set it equal to f of b, then I should end up with a equals b, right, at the end. But we're not going to do that. I'm skipping straight to the fun part, right? And so we can check, right? We can check to see if, oops, sorry, it's lagging here. We can check to see if a function is 1-to-1 just using the graph, right? And what we use is called the horizontal line test. So remember we used the vertical line test to see if we had a function, right? So then we were checking, okay, if I do vertical lines, right? Then I'm checking to see if I have a function. So both of these are functions, right? Because I can intersect the graph at any point here. And at any point, any vertical line is only going to intersect the graph once. Now, if we're checking to see if it's 1-to-1, then I can use the horizontal line test. So what I want to do is I want to be able to draw horizontal lines all across here. And as long as I'm only intersecting the graph once, right? Whereas here I'm intersecting twice. In fact, I'm intersecting twice for all values of x except for 0. If I'm intersecting the graph more than once horizontally, the graph is not one-to-one. Okay, so recall the vertical line test. Any vertical line only intersects the graph once if it is a function, right? So I want to highlight, okay, the vertical line test is testing for whether you have a function. And I guess I have the definition here, so why not just use it? To determine if a function, right? So notice that it has to be a function first, right? To determine if a function is one-to-one, we use the horizontal line test. So if it's one-to-one, we use the horizontal line test. And I'll bring that definition in here. Okay. So I want you to use the horizontal line test to tell me if it's one-to-one. But I also want you to read questions carefully, because sometimes, especially on the final exam, right, I might ask you, is this a graph of a function, right? So I give you a graph and you have to use the vertical line test to determine if it's a function. Or I might say, hey, is this graph a one-to-one function, right? Yes or no. And then you'd have to use the horizontal line test. So it just depends on you have to read the question carefully, right? Because there's really only the tiny distinction between asking for a function, whereas asking for a one-to-one function. Okay. So a horizontal line, I had a hard time before, a long time ago now, it feels like, but I do remember struggling with, okay, so vertical versus horizontal, but if you just think of the horizon like this, right, then it's horizontal like this, and then the other one is vertical, right? And so whatever you have to do to kind of remember these things. So let's do a couple of examples here to try to figure out if we have, I'll put it in the middle, a one-to-one function. First thing I want you to do is let's just make sure that all of these are functions, right? And so here I can draw vertical lines, right, straight up and down at any point, and at any point here, right? We can do a rapid fire check to see if these are all functions. Yes, they are, because it doesn't matter where I intersect. There's kind of something fishy going on here, but it does extend out. So, okay, so these are all functions, right? So that's a good start. We can use the vertical line test to make sure that these are all functions. Now, what you want to do is we want to find if this is a graph of a one-to-one function. So now I want to use the horizontal line test. And if I can find any point where my horizontal line crosses the graph more than once, it's not one-to-one, right? So here, let's see here. And maybe I'll do. All right, well, it looks like I can draw a line like this. making it not one-to-one, right? So this one is not one-to-one. And I'll just do a little X here. How about 8? Well, it looks like I can draw horizontal lines at any point. You'll want to be careful here where it kind of flattens out. But as long as it looks like it's still decreasing, then you're okay. So it is a one-to-one function. And same thing with 9, right? It looks like I can, well, they ended up kind of on a slant there, but it looks like I can draw horizontal lines there and still only intersect the graph once. Now, I want you to keep an eye out for things like this, right? And just kind of convince yourself that, okay, for it to be one-to-one, I can only get to the output from one input. But here, this whole region is a problem, right? Because for that whole length of X, I'm getting the same output, right? So from X's, from here to here, I get the same output, right? So this is not a one-to-one function. So I want you to keep an eye out for those straight horizontal lines. Okay. Just like we did with vertical asymptotes for functions. Yeah. So same thing with 11. If I draw kind of here, things got weird there. Maybe I'll zoom in and see if I can figure out. Right, so it looks like maybe I've got some trouble here, which I didn't actually think before. Something like that maybe looks straight-ish. Right, so it looks like I can find spots where it's not necessarily passing the horizontal line test. So I'm going to go ahead and say no. Whereas here, I'm drawing horizontal lines all the way across here. I think initially I said it was okay, but now that I'm looking closer at 11, I'm thinking no. On the test, when I get you to do this, it'll be obvious. Right? There might be something like this going on. I do want you to keep an eye out for that, but not something kind of minute like this. So here it looks like I can draw horizontal lines and everything is hunky-dory. So I'll say it's one-to-one. Jury's still kind of out on the 11. I think I'm seeing two output, or the same output for two values of X, but I'm not sure. Okay, so I want you to be able to use the horizontal line test to determine if a graph is one-to-one or if a function is one-to-one. It has to be a function first. All right. So let's talk about the inverse of a function, and then eventually we'll start finding the inverse of a function. But there's a couple of cool things that we need to talk about first. So the inverse of a function is basically the function that you can apply to undo the original function. So it assumes that we have a one-to-one function, right? That's what we established initially, is we said, okay, well, I have to have a one-to-one function in order to find the inverse. We haven't talked about the inverse yet. We're about to, but the first step is determining that you have a one-to-one function. So here, let f be a one-to-one function, right? So that's why it's important that we know how to identify one-to-one functions. And here's kind of a fun part with domain A and range B. Range, remember, is all the possible outputs. which can be kind of hard to determine, right? And so you have some domain. The domain is relatively easy to find. We've practiced quite a bit. And then the range, all the outputs, is a little bit trickier, right? Kind of harder to wrap your head around. But then it's inverse function. And how we denote the inverse is f to the negative 1. Okay, so f to the negative 1 of x, you're going to read as the inverse of f of x. Okay, and just kind of a big glaring note here. Note that f to the negative 1 of x is not the same as f of x to the negative 1, right? F of x to the negative 1 is the reciprocal, right? So that's 1 over f of x, right? Whereas the inverse is going to be its own function, not necessarily the reciprocal. Okay? So just keep those two in mind. So if the power of negative 1 is on the f, then you're talking about the inverse. If it's on the outside, then fine. Then it's to the negative 1, which bumps it down to the denominator. So you need to keep those straight. But of course, we'll say stuff like find the inverse. Okay. So the inverse function, and here's where it gets kind of cool, has a domain of b, but remember the range of the original function was b, right? And so they kind of swap, right? Which makes sense. They are well, they're inverses of each other, so they kind of undo each other. So then if I say that, okay, the inverse has the domain of b and a range of a, well, it's easy to find the domain, right? I'm going to go as far as saying it's easy to find the domain, right? So if I can find the domain of the original function, and then I can find the inverse, right? If it has an inverse, well, then that's the range of the original function. And then, of course, I know the range of the inverse because it's the domain of the original function. Okay, so notice the interesting property that if you have some function f has the domain A and range B, then f inverse has domain B and range A. Right? Since finding the domain is, I'll even say it, a lot easier than finding the range, we can find the domain of the inverse, and then that is the range of the original function, right? We can find the domain of f inverse to find the range of f, assuming that it's invertible, of course. Assuming f is invertible. Okay, so it's just kind of a neat property that we're not gonna leverage as much as we probably should. But if you are able to find an inverse, so make sure that it's one-to-one, make sure your function is one-to-one. And then if you're able to find the inverse, you'll be able to find the domain, and then you'll be able to say, well, that's the same as the range, right? So kind of a neat trick. Now, what else? What other neat tricks do we have? We've got the inverse function property. Okay. Now, what does that say? If I'm going to let f be a one-to-one function with a domain A and range B, kind of a typical setup, then the inverse function satisfies the following cancellation properties. These are function compositions, right? And so what we're saying is that if I take the inverse composed with the original function, right? So how we can rewrite this is, well, this is the same as f inverse composed with f of x. Well, what's going to happen if I take those function compositions? I should end up with x, right, for all the x's in the domain. We kind of ignore that part. But also, and you have to show both ways, if you take the function, the original function composed with the inverse, it should also land you at x. So it should just simplify to x. So it's kind of a neat property. So you've got f composed with f inverse of x. Yeah. So if you have calculated the inverse, right, which is f inverse, and you want to check your work, right, then what you can do is you can make these two compositions and make sure that they cancel to just equal x, right? So if you've calculated the inverse, you can check your work. Check your work by confirming that f, and it doesn't matter, right? We're doing both. So if you want to do f composed with f inverse first, because that's what I usually do, equals x, and, right, f inverse composed with f of x equals x. It's usually enough to just check one, but technically both of these have to check out, right? And so you need to do both in order to check your work, right? To really check your work. If you're satisfied, and I'm just offering this as a way to check your work. So if you're satisfied after one of them, then that's fine. But we need to check both, okay? So let's do an example. We haven't found the inverse yet. So here they're just giving us the inverse. Use the inverse function property, which is this, right? That all of these two compositions, they both have to cancel to x, okay? To show that f and g are inverses of each other. So here we're told that these two are inverses, okay? And we want to show that they're inverses of each other. I'm gonna do one thing that I will mention that I won't get you to do is work with restrictions on the domain, right? So 43, for example, says that for f of x, x has to be greater than or equal to 0, and for g of x, x has to be greater than or equal to -9. I'm not going to make you work with those restrictions. So let's do one like 40 maybe. Okay. So 40, right, you have to confirm that these two are in fact inverses of each other. So we've got f of x is 2 minus 5x, and we're told g of x is 2 minus x over 5. Okay. So to confirm f and g are inverses of each other, it doesn't matter which one we call the inverse and which one we call the original function. If they're inverses of each other, then they have this kind of mirror property. So to confirm f and g are inverses of each other, we need to show that both of these function compositions work out. So we need to show that f composed with g of x equals x, and it's really important that you do both. G composed with f of x is also x. Remember what we said? We showed earlier that f composed with g is definitely not the same as g composed with f, right? And so that's why you have to check both, okay? Need to check both. Okay. It's important. So what I usually do is, with a little bit of luck, I'll be able to split my page and then I'll be able to run them side by side. Mostly because otherwise it's a lot of scrolling on the iPad, but even on paper, right? It's nice to be able to kind of see them work out next to each other. So what we're going to do is I'm going to do f composed with g of x up here, and then I'm going to do g composed with f of x over here. And then I'm just kind of going to imaginary, oh, I didn't split the page kind of in half there. Okay, so I kind of work them side by side, and definitely when we're working in person, I know a lot of people fold their page over or something like that just to kind of divide the page up a little bit. So f of g of x, we know how to do, right? So whether you want to do f first and then substitute in the g, that's fine, or substitute in the g and then put it into f. I'm going to do 2 minus 5 times g of x. We know how to do these function compositions, and so this is a really good way to make sure that you know how to do function compositions, right? So I definitely do this on a test where I get you to confirm that these two are inverses, and you do have to show all your work. So, and then I mark your work. So just heads up that you will have to do this. So that becomes 2 minus 5 times g of x, which is 2x minus, or 2x over 5. Or, sorry, 2 minus x, let me just confirm. 2 minus x over 5. Okay, looking good, right? And so here, right, I see that I can already cancel these 5s. That's breezy, right? So I'm going to cancel these 5s, and then I end up with 2 minus 2 plus x. 2 minus 2 is 0, so I end up with x. That's a good start, right? Because I want to show that does it equal to x? So sometimes if I'm checking to see if something equals x, I'm hesitant to say that it equals x. I want to know, does it equal x, right? And so here, I'm going to put a little green smiley face here because I'm happy with that result. I still have to do the other side, right? I still have to do g composed with f. So let's go ahead and do that. And what we're checking is, does it equal x? So, oops. G composed with f of x. So now I have 2 minus f of x over 5. Where f of x was 2 minus 5x. So let's see here. Yeah. So I have 2 minus 5x over 5. I can already see that this is going to cancel to 5, but if I expand this out, I get 2 minus 2 plus 5x over 5, putting me at 5x over 5, which is just going to go to x, which I'm also happy about, right? So what I'm going to do is I'm going to write a little blurb here, right? Since f composed with g of x equals x, but that's also the same as g composed with f of x, we can conclude that f and g are inverses of each other. Are inverses of each other. Okay. So definitely try those other ones, because and maybe skip the ones with restrictions on the domain. In fact, don't need to deal with restrictions on the domain. I'll say for now, don't worry about 43, but see what you can do about these other ones. Okay. Sometimes you'll have to bust out all your fraction knowledge, right? Finding that common denominator, and then slowly things will simplify, right? And so you might need to draw on some of that. Okay, so let us go ahead and actually find the inverse of a function. So how do we find the inverse of a function? We've talked about, okay, well, in order to have an inverse, it has to be 1-to-1, right? And we can check that we found the inverse by using those compositions that we just did. And so now all that's left is actually finding the inverse. So if you go to the second page, there is an outline here. Okay. So how to find the inverse of a 1-to-1 function? First, you're going to write y equals f of x. So you'll probably be given some function f of x, and you'll want to find the inverse of it. So first thing you're going to do is place your f of x with y. That is fine, right? You're going to solve this equation for x in terms of y. So we're usually solving for y, right? We're kind of programmed to solve for y, or at least I am or was. But now we're going to solve for x in terms of y. Okay, so we're going to rearrange and solve for x. Okay, then you do a switcheroo. So now you switch out x and y. And so once you've solved for x, then you can switch those and say that, okay, the resulting equation is the inverse, right? Because you've swapped your x's and y's. So now your y is the inverse as a function of x. Okay. Sometimes what I'll do is, and it depends on what you've done in the past. So for me, I was taught I was taught that you switch your x's and y's and then solve for y, right? So, or alternatively, you can too swap x and y and solve for y. And then y is the inverse of f of x. It doesn't matter which way you do it, right? You can play around with both, or if you have some vague memory of maybe you swapped your x's and y's and then you solve for y, that's fine too. I'll know what you mean, right? But I'm gonna follow this procedure, even though in my mind, I was taught this procedure, so that's my go-to. But because this is what they do here, then let's just follow their procedure. So what are we gonna do? Let's just do some practice problems. Okay. So again, there are a few where you've got restrictions on the domain. So here, let's see here. Right, 61, 62, 63, 64, and 70. Right, you can ignore. Oh, I guess it's bigger. Ignore questions with restrictions on the domain. It's not something that I'll not test it. It's not something that I'm expecting you to deal with, although I mean might be fun to give it a try. I'm just gonna leave them alone. Okay, so if you want to, you can do them, but don't worry about them. Okay? Because it adds that added kind of layer of, oh, okay, I have to think about the domain. Usually they have those restrictions because those are the restrictions that you will need in the inverse, right? But I'm just going to ignore them for now, or forever, in fact, at least in this course. Okay, so here, let's kind of focus our attention on 49 to 60 seems reasonable. Okay. Noticing that a lot of these functions look the same, right? So here we've kind of got these baby functions, and then after 57 to 60, we've grown up to kind of bigger functions. So let's do a small function first, and then we'll grow up to a bigger function. So let's do 53 first. If I have f of x is 1 over x plus 2, technically, you should graph this in Desmos, make sure it passes the horizontal line test. It will, because it's just asking find the inverse of these functions. So it is invertible, it is 1-to-1, and we're just going to find the inverse. Okay. So now remembering those steps. So step 1, regardless, is write y equals f of x. So replace your y with f of x. Step 1. Y equals 1 over x plus 2. Okay. Step 2. Solve for x. So if I'm solving for x here, I've got x plus 2 in the denominator. Slowly but surely, I want to move stuff over so that I've just got x on one side. To do that, I'm going to need to multiply both sides by x plus 2. So this puts me at y times x plus 2 equals 1. trying to solve for x, right? Remember, you're solving for x. What I'm going to do is I'm going to divide both sides by y. So then I get x plus 2 is 1 over y. I don't need those brackets anymore. And what I'm going to do is I'm going to subtract 2 from both sides. So I get x is 1 over y minus 2, noticing that the minus 2 is not over y, right? So the order here of the order of operations is going to be really important. Step 3, interchange x and y. Then y is f inverse of x. Okay. So first thing I'm going to do is I'm going to interchange my x with a y and 1 over x minus 2. Therefore, f inverse of x is 1 over x minus 2. Okay, so we have a couple of ways that we can check our work, right? We can check our work by using our compositions, right? We could say f composed with the inverse that we just found, does it equal x, right? And then the inverse composed with f, does it equal x, right? We can check it that way. Or we can also check it graphically if we want to, right? And so we have 2 ways to check that this is indeed the inverse. The first way is to prove that f composed with f inverse of x equals x, and the inverse composed with the function is also equal to x. Right? Or our second option is we can check it graphically. I sometimes have a kind of a hard time with seeing graphs, right? Where are they reflecting? But let's just check it out, and then we've covered all our bases. Graph f of x and f inverse of x, and show that they're reflected around y equals x, and show that they are reflections around y equals x. So I'm going to bring in that blurb from the handout just so that we have seen it. Okay, so the graph of the inverse is obtained by reflecting the graph of f in the line y equals x. So if you have the functions, then you can graph them, and you can make sure that they're reflected around this diagonal line. To me, sometimes that's hard to see, but let's just do this in Desmos and see what happens. So my original function was what? F of x was 1 over x plus 2. Okay, so I'm going to graph that first, and then I'm also going to graph 1 over x minus 2. I'm going to try to remember these here. Okay. Oh, secant of x, not there yet. I want to do 1 divided by, and then x plus 2, I'll use brackets, oops. X plus 2, I want to make sure that it stays in the denominator. And then my second function, I found 1 over x and then minus 2. Okay. little bit weird to see, right? So what if I do a y equals x line here? Okay. Like I said, I have a really hard time seeing this. So it's okay if you're not seeing it. I don't see it. It's there, it's true, it's happening. What we found was in fact the inverse. But if we go kind of, you can try to convince yourself that this black line here, right, is being reflected here. Where? Like I said, I'm struggle sitting with this stuff. It is something that you can use. I will always use the function compositions if I'm doubting myself, right? So for me, it's easier to use the function compositions because that's just math. Here, I have to really think about, okay, so this value here is reflected to, I guess, this value here. Who knows? But it's supposed to be a reflection. So for me, I know that wasn't very helpful, was it? But for that reason, for me, I will always just use the function compositions if I'm unsure. Okay. So here I'll say, right, I usually have a hard time seeing this in graphs. So I prefer to use function compositions to check my work. Right, but it is an option and it's there if you see it, right? So the idea is here at BA, you end up at AB on the inverse. I have a hard time. I don't see it, or unless it's super obvious like here, right? But when we have things that are crossing over, then I know I'm lost. That's okay. I have other ways to check my work, right? I have these function compositions, right, that I can do, and I find that they're very reliable, and I like doing them. They're really fun. So let's find another inverse. Let's do one that's a little bit trickier. Oh, and I think I have the questions already in here. Okay. Let's do 59 together. So I want to find the inverse of this thing. Find the inverse. Okay. So again, I'm going to break it up by steps. And so my first step is to replace f of x with y. Easy enough. Step 1 is we're going to write y equals 2x plus 3 over 1 minus 5x. This one's a little bit trickier, right? Because notice that I have an x in the numerator and an x in the denominator, right? So this is more something that I'm going to be expecting you to work with. Okay. All right. Step 2, I'm going to solve for x. Step 2, solve for x. Easier said than done sometimes, but same idea. I want to bring this 1 minus 5x up to the left-hand side. So I'm going to multiply both sides. And so I get y times 1 minus 5x is 2x plus 3. Now I'm solving for x. So I need to make sure that I kind of do that carefully. To me, because I have an x over here, what I'm seeing is it might be easier if I just expand this y inside, because then I'll be able to move this 5xy around and just kind of work with that. So this becomes y minus 5xy is 2x plus 3. I'm going to do a switcheroo here where I move this y over to the right-hand side, but also move this 2x over to the left-hand side. So this becomes negative 5xy minus 2x is 3 minus y. Okay, so a couple of things I could do here. There is a common negative. I'm going to leave that negative in there. And I'm just going to pull out the common x's, right? So because I'm solving for x, I want to try to extract the x as kind of one block. So I get x times negative 5y minus 2 is 3 minus y. If you wanted to, you could have pulled out a negative x, right? Which would make 5y plus 2 in here. Right? Maybe that's nicer for you in your mind, or maybe it's just easier to think about. I kept it in. It doesn't matter. We're going to end up at the same answer, but maybe I'll do kind of an or. What we could have done, negative x times 5y plus 2 equals 3 minus y. Just doing them kind of side by side here. Giving you a couple of options, right? Showing you that we end up at the same place. So then if I'm solving for x, well, x is going to be 3 minus y over negative 5y minus 2. Right? Or negative x is 3 minus y over 5y plus 2. So x then is negative 3 minus y, and that negative is all out front, times 5y plus 2. Oh. You can extract that negative here as well, right? So whether you want to keep it like this or extract that negative, you can. So x is, reminder time, is 3 minus y over negative 5y plus 2, but this negative behaves the same if it's down in the denominator, if it's all out in front, or if it's on the numerator, right? 3 minus y in brackets there. So this becomes x is negative 3 minus y over 5y plus 2. Either way, right, we end up at the same, in the same spot. So doesn't matter how you do it. So then step 3 is to switch your x's and y's again, and then the result is the inverse. So then step 3, interchange x and y. Y is now the inverse of f. So what I get is, notice that these brackets around the 5y plus 2 aren't doing anything anymore, so I don't need to write those. So I get, I'm interchanging. Y is negative 3 minus x over 5x plus 2. So then the inverse is negative 3 minus x over 5x plus 2. That is great. Okay. So what I want you to do is, there, we did it, inverses and all. So that's the end of chapter 2, okay? And so I want you to try more of those, finding the inverses, maybe doing some function compositions, right? Really practicing this stuff, because it can be hard in the beginning, but once you've done a few, then it'll make it easier. So this is the end of chapter 2. That's great. And I think that's a great place to start. I'm not going to start chapter 3 now. That's insane. If you have any questions, let me know. Otherwise, I hope you have a great weekend, and I'll see you on Tuesday.